Okay, welcome back. This is oral 1.2b, Multi-View Geometry 3D Scene Understanding. I'm Ko Nishino from Kyoto University, and I'll be chairing this session with Yonja Lee from UC Davis. So we'll have 3 talks in succession, 5 minutes each, followed by 3 minutes of Q&A. And there are a bunch of mics around you, so you can come up and ask questions. Or you can also use Slido. So log into sli.do and enter the event code ICCV19_D2, and you can type in your questions there, and you can also upvote good questions. So we will select sections from questions from there to ask the authors. If you choose to ask your questions in this room, please remain in your seat until the 3 talks for each group is finished.
Oh, and I just want to add one thing. So if you haven't used Slido before, there was an email sent out this morning by the ICCV, I guess, program chairs, which is titled ICCV 2019 Prepare for the Main Conference. So in that email, there's also instructions on how to use Slido to post and vote for questions.
Okay, so we'll get started with the first 3 talks.
I'm Pablo, and this is a joint work with Johannes, Schönberger, Sudipta, Sinha, and Marc Pollefeys on privacy preserving image query for camera localization. Given a query image and a pre-computed map of the scene, the task of computing the 3D position orientation of the camera is called image-based localization. This is a crucial task behind many modern AR devices. All these devices need to know their precise position orientation within the world. Localization runs continuously as a background process that AR users might not be fully aware of what is being recorded by these devices. This can potentially lead to a serious privacy concern for which there are no existing solutions. Recently, Pitaluga and all presented a new way to compromise privacy, showing that the pre-computed map can be inverted to reconstruct detailed and recognizable image of the scene. To address this problem, we recently presented at CVPR the first method for privacy-preserving image-based localization, where we propose to conceal the map while still allowing precise localization. But in current commercial camera localization service are cloud-based, so in this case the map remains stored securely. But the new user's images are sent and processed in the cloud. For example, a client takes an image and then compute the features are sent to the cloud. The server computes the image in the map and returns the post back to the client. But then the problem is, from the feature, an attacker could potentially recover the original image. So our goal is to hide or obfuscate the query image in such a way that we prevent image inversion on the cloud, but still allowing localization. So here a key insight. 2D points can be interpreted as an intersection of 2 arbitrary 2D lines that are back projected to 3D planes. But by removing one of these planes, we remove one of 2 constraints for camera localization. And by combining multiple measurements, we can still estimate the camera pose even though we don't know the precise position of the original point. In a real example, our proposed solution to conceal the image feature is to select a random line passing through each point feature, discard the point feature location, and upload the 2D lines plus the script to the cloud. The traditional method to solve absolute pose is P3P with minimal trig correspondences. But by using 2D lines, one of 2 constraints for camera localization are used, only one. So we need double 6 correspondences in the minimal case. Our method gets translated to a point-to-plane problem. Additionally, we propose several variants of our method leveraging existing minimal solver. Some of them are computationally efficient, being a practical solution. So in our previous paper at CPR, the map was the only confidential entity, but now we are also proposing an extension that considers confidential querying and confidential map altogether. So what gets revealed after localization? In the traditional method, all the features are accessible for the inversion technique, revealing all the information in the picture. But in our method, only a portion of features gets revealed after localization. Notice that the only points that which gets revealed are those that from a static object. Objects that were present on the scene at the moment the map was created. Some examples to clarify this. On the left, the original image. On the middle, the reconstructed image using all the features. On the right, a reconstructed image using only the revealed feature. As we can see, the inversion technique can only revert the static objects that were present in the map, but the transient objects such as people are well concealed. Here are some examples on accuracy recall curve for rotation and translation error. This result basically shows that our method behaves similar to P3P, the traditional method. There are obviously some trade-offs because we are using less constraints. We also tested in internet photo collection datasets, and again we show similar results on P3P. So the conclusion, we have introduced a privacy-preserving localization method that conceals the image query. We can also handle confidential queries and maps together. Our method translates to a system minimal software, and most variants are computationally efficient. Thank you very much.
Hi everyone, I'm Songyou, and today I'm going to present Calibration Wizard. To do camera calibration, most people just randomly capture images and with finger cross hope to acquire accurate intrinsic parameters and like focal length and distortion. However, we observe that inexperienced users usually are not able to take images which lead to high accuracy. Therefore, we propose a system that guides the user through a simple user interface in order to move the camera to poses that are optimal for calibration of camera. As shown here, the proposed next best camera pose is displayed on the screen, and the user only needs to move the camera toward this pose. And our proposed approach computes the next best pose, which will add most information over the already available images. This works as follows. In camera calibration pipeline, assuming the reproduction error has been minimized for the previous images, we can then calculate its Jacobian matrix, the information matrix, and its inverse. And what we are interested in is actually the submatrix in this inverse matrix. We call it sigma, which corresponds to the covariance matrix of intrinsic parameters. And finally, we globally optimize over the trace of this sigma with respect to next pose. And this is how we get the optimal next pose. And here we propagate the uncertainty to each pixel on the image area. And we can see that our method is outperforming. Here are some sample images taken during calibration. Compared to freely taken images, our wizard suggestion images indeed correspond to poses often chosen by experts, which reach the image border with large inclination along the viewing direction. However, the wizard images are sometimes extreme with strong grazing viewing angle relative to the checkerboard, so corner detectors usually fail in this case. This problem may be avoided by considering the expected uncertainty of the corner extraction. Let me explain this in detail. So consider these simulated corners. And the further the opening angle is away from 90 degrees, the higher the uncertainty is on the extracted corner position. Here, the corner uncertainty is computed directly from the autocorrelation matrix. And we simulated a corner of different opening angles and blurriness, and then feed polynomial functions, and that maps the angles to the coefficient of the autocorrelation matrix. For hypothetical next pose, we can compute the expected autocorrelation matrices and include this in the computation of the information matrix. This is a principal way of including corner uncertainty in calibration. And we first evaluate our system by designing a synthetic experiment where we fix the intrinsic parameter and generate a random camera poses. After initialization, we compare the calibration from wizard images with these images generated from random poses. And the graph shows the mean and standard deviation of the predicted focal length. Apparently, the uncertainty, the calibration from our wizard images converge much faster and more accurate than the random poses. Here we show the result on the radial distortion parameter K2. Considering large distortion now, randomly taken images fail to converge, but our methods still work. So we also test on real-world structure from motion experiments on a carved wooden bed. We put the first and the last image of the sequence as identical. If calibration is accurate, the structure from motion without loop closure should return similar poses for these two images. And the distance on the 2D projected point can be reflected, can reflect the calibration accuracy. As shown here, our method provides comparably lower error with even fewer calibration images. To sum up, we develop a system which can guide users to acquire accurate calibration results from only a small number of images. And we have also shown how to incorporate uncertainty in a normal principle manner. And thank you.
Hello, my name is Tobias from Mercedes-Benz, and I'm going to present our joint work with Algolux about gated to depth, real-time dense LiDAR from gated images. As the sensor setups of many self-driving car prototypes show, active depth imaging with LiDAR systems is crucial for safe autonomous driving. LiDAR is an essential cornerstone image modality, but it is expensive, offers low spatial resolution, and suffers from backscatter in adverse weather conditions. For 3D perception, there exists a variety of sensors and algorithms. Passive vision performs poorly at large ranges and fails when ambient light is not sufficient. While a scanning LiDAR has limited resolution, upcoming spattle flash LiDARs are highly photon inefficient and suffer from pile-up distortions at higher pulse powers. Correlation time of light cameras are currently limited to only a few meters in outdoor scenarios. In this work, we present an imaging framework which converts 3 images from a gated camera into high-resolution depth maps, with depth accuracy comparable to pulsed LiDAR measurements. It is low cost for long ranges, strongly suppresses backscatter, and provides dense depth information at camera resolution. Gated imaging is an emerging sensing technology in readily available CMOS that sends out pulsed illumination and integrates the scene response between temporal gates. On account of the speed of light, only photons from a certain distance in the scene can be captured on the imager, which strongly suppresses backscatter. Suppose that a car is located at a certain distance. By using multiple broad and overlapping slices with different range intensity profiles, the car appears in different grayscale values in the respective slices. This correlation enables precise depth estimation based on gated images. State-of-the-art automotive datasets do not contain gated images. Therefore, we acquired the first long-range gated dataset by driving over 4,000 kilometers in Northern Europe. We captured around 70,500 images during night and day and in various weather conditions. However, only sparse ground truth depth from LiDAR is available. In our work, we propose a network architecture that takes 3 gated slices as input and generates a dense depth map at the same resolution. The generator is a simple multi-scale variant of the popular unit with skip connections. We train our proposed network to minimize a 3-component loss, namely multi-scale loss, smoothness loss, and adversarial loss. In addition, we use synthetic data for training a patch-gen discriminator to improve accuracy and make the approach more scalable. In order to obtain full image ground truth depth, we simulated gated images based on a GTA 5 computer game. First, we extract the diffuse reflectivity and transform it by an empirical model to the infrared domain. Then illumination and shadows are calculated and combined with the infrared reflectivities. Finally, we apply the gating and the noise model that have been calibrated on our real camera, and we obtain 3 gated slices and full ground truth depth. In total, we simulated around 10,000 samples with continuous ground truth depth and have recorded around 14,000 real gated images in clear weather with sparse ground truth depth from Lidar. In this video, you see the performance of our proposed architecture when trained on simulated images. Our method achieves high resolution depth and captures fine-grained details of a scene at both close and far distances. For transfer learning to our real dataset, we use the pre-trained weights of the generator for fine-tuning, and we compare our approach with numerous state-of-the-art methods such as stereo, monocolor depth, and Lidar depth completion. Our method achieves best depth accuracy comparable to scanning Lidar systems. By using only 3 gated images, gated to depth is able to capture dense depth maps that offer significantly finer details compared to sparse Lidar, especially around pedestrians. These videos show that our method works at day and night. In summary, we turn a CMOS gated camera into a cost-sensitive, high-resolution dense flash Lidar and validate our approach in simulation and experimentally on outdoor captures. An interesting direction for future research is the inclusion of RGB data for areas with low illumination and end-to-end semantic scene understanding. Thank you very much for your attention. Our data and code will soon be available, and we are happy to meet you at our poster number 23.
Okay, do we have any questions? Please come up to the mics. Okay, I'll start with one question for the third author. If you can vary the gating slices, how would you optimally decide when to, gate and capture? And it seems like it should be speed dependent. And then can your network actually take in varying offsets?
Yeah, so currently we use only one setting for the gated slicing, for the gated slices, and it's just one first design how you can do it, but of course you can do a lot of optimization. You can try to find via optimization the perfect profiles for depth estimation, the perfect profiles for certain speed. So I think there's a lot of potential what you can use, and in addition that might be it is also important that you can apply it on the gated camera, so the hardware is limited. You cannot do everything, but you can do a lot.
Yeah.
Okay, so question for a third paper. So how do you synchronize multiple systems to reduce the interference?
Yeah, so that's actually a big problem. We haven't tested it so much. But the good thing about this gated imaging is that you use very short exposure times and very short illumination. So we are in the area of hundreds of nanoseconds. But of course, you can try to do things like using a little bit different wavelengths, for example, or you can do it, you can think about it as, for example, for the radar systems. I think 10 years ago it was a similar problem for the radar, but in future there might be also solutions which you can use for gated imaging.
Okay, thank you.
Any other questions? Okay, let's thank the speaker again.
Hello, everybody. I'm Andrea Nicastro. I will be presenting cross-section prediction for enhanced RGB-D fusion, a work done with Ronnie Clark and Stefan Leutenegger at the Dyson Robotics Lab at Imperial College of London. Depth-only fusion yields incomplete reconstructions, and we propose a method to predict and fuse additional information on the objects. We predict thickness at level per pixel as the distance between two consecutive surfaces. There are several advantages, like it is compact, as in 2D representation, has a clear geometric interpretation, and it's compatible with traditional reconstruction algorithms. To train our network, we render the thickness of the objects in Blender with a custom shader, and we present two datasets, one purely synthetic, based on YCB, and one partially synthetic by aligning synthetic model to real RGB and depth to fine-tune our model. To recover the thickness for all the objects in a scene, we propose the use of multi-stage pipeline. The first stage, we predict masks and bounding boxes with mask CNN from RGB, and then we use it to crop the single objects from the depth frame at the second stage of the pipeline. The depth for each object, we pair them to the binary masks or silhouettes, and then they are input to our proposed network cross-section. It is a fully convolutional network based with a encoder-decoder structure based on ResNet, fully 2D, that predicts the thickness of the objects. And then we use all the information detected at the first stage of the pipeline, as again, bounding boxes and silhouettes, to compose a thickness frames that jointly with the depth allows us to recover the 3D shapes of the scene. To recover the 3D shapes, we propose a use of an enhanced TSDF, here shown on the right, that considers the new predicted information. On the left, we can see an example of plot that is of an object 2 meters thick and 1 meter distance from the camera. On the blue dashed lines represent standard TSDF. The continuous red line represents our proposed one. We can see that it correctly classifies the internal part of the object occupied, and there's 2 zero crossing values for the two surfaces represented by our network. The final results, with these we can recover most of the 3D shape from one single image. As we can say, this is the front surface, while the back surface is actually quite accurately reconstructed. But with using integration in a Kinect fusion style, we can also integrate multiple frames and multiple prediction. As we can see on the left, we can see our results, while on the right, we can see depth-only fusion. Numerical evaluation on YCB video sequences not using a training time shows that we can recover, we have twice as much intersection of a union and recall with respect to the depth-only fusion, while preserving a similar precision. On the blue dashed line represents is depth-only fusion, while the red solid one is our approach. And the numbers on the bottom, we can see the number of frames integrated. In a comparison against voxlets, we can see on the here, top left, that our results has comparable quality, showing general ability, even though if it's only training on YCB and YCB video. This is, of course, backed up by numerical evaluation, in which we can, on the assumptions that all objects are detected at the first stage of the pipeline. In conclusion, we present the use of cross-sectional thickness as an approximation of 3D shapes, a TSDF function that considers it, 2 datasets to train the network, a complete pipeline to recover the 3D information from RGB-D data, an extensive experimentation on tabletop scenes, and code to train, test, and render new data that will be released soon. Thank you for your attention. For any question and critics, please come at post-it number 24.
Hello everyone, my name is Stefan. I'm a PhD student at the PFL, and this work was done during my internship at Amazon Tübingen. So in this work, we work with the event-based sensor. The sensor is very good for robotics applications. It basically records asynchronous events of brightness changes. For example, take a look at this unevenly rotating disk with a black dot. If it rotates fast, event sensor captures a lot of events. However, if it rotates slowly, it captures just a few events. Every event is characterized by 2 discrete coordinates and special coordinates and 1 temporal continuous coordinate, and binary polarity, which indicates the sign of the brightness change. The problem is that modern computer vision applications rely on neural networks. which works with the discrete data. Of course, we could discretize time domain, but this will result in a prohibitively large tensor. The common approach nowadays is to use some handcrafted transformation to aggregate events across time into so-called event image. For example, we can count number of positive and negative polarity events in every location. However, in this work, we try to understand if we can actually learn temporal aggregation instead of handcrafting it. In particular, we are interested in stereo reconstruction from event-based camera. This slide shows our architecture. It's based on our previous network for the frame-based camera, which has large receptive field and allows reconstruction for location without events. And we had 2 blocks to handle events. Event queue, which stores events for every location, most recent events for every location, and temporal aggregation module, which performs aggregation across time. So in the next slides, we explain every block. So event queue is first in, first out queue, which stores most recent events. It has 2 parameters: capacity and time horizon. Capacity tells us how many events at maximum we can store in every location. And time horizon tells us for how long we store every event. So having events stored, we then perform temporal aggregation using a continuously fully connected layer, which we propose. Let's compare it to the conventional fully connected layer. In the conventional fully connected layer, the weight of every input computed based on its index and input vector. However, in the continuous fully connected layer, the weight is computed using timestamp of the input, using kernel network. So the kernel network takes timestamp at compute weight. And the kernel network is a multi-layer perceptron, and it basically implements the continuous kernel. This allows us to handle events with a continuous timestamp. Next slide show our results. So firstly, we experimented, we added our temporal aggregation to the stereo network with the small receptive field, and it was clear that by increasing capacity, we could get better results. Temporal context was very useful. However, when we added temporal aggregation, our temporal aggregation to the network with a large receptive field, it basically became insensitive to the temporal context and relied more on spatial context. However, we believe that in other datasets and applications, the temporal context still can be useful. The next slide shows our benchmarking, comparison of our stereo reconstruction method to other methods. So we can see that on sparse ground truth, our method greatly outperforms other methods, and it's also the only method which can produce dense results. The next slide shows qualitative results. On the left image, of course, we show events overlaid with the grayscale image, but the grayscale image, of course, is not available to our algorithm. And the right image shows estimated depth. So thank you for your attention, and please stop by our poster.
So hello everyone, I'm Richard from Tsinghua University. Today I'm going to introduce our work, Point-Based Multi-View Stereo Network. The target of multi-view stereo is to reconstruct the 3D shape from a set of images and the corresponding camera parameters. Recently, learning-based MVS methods have shown great success. By using learned features, they can get more robust matching, and by learning shape prior, they can achieve more complete reconstruction. One key component of this method is the 3D cost volume. I'll first give a brief introduction to the cost volume-based method to show the advantage and limitation. In order to estimate the underlying surface from the viewed images, a 3D coarse volume is built in the frustum of reference view. For each voxel in the volume, features are fetched from all the views through projection. The main intuition is that the image appearance at the correct depth should be consistent across views. Based on these previous methods, use dense 3D CNNs to predict the occupancy of each cell. The main limitation of the coarse volume-based method is that the memory consumption is cubic to the resolution. Therefore, these methods are not feasible for high resolution and accurate reconstruction. One question is that, are all these 3D CNNs necessary? Actually, the depth map is just a curved surface in the 3D space, and most of these 3D counts are applied in areas far from the surface, which are not necessary and do not help the final depth prediction. Based on this observation, we use point cloud to represent the curved surface and process the surface points directly. Therefore, we call our network point MVS-NET. Compared with voxels, point cloud is more suitable and efficient to represent the sparse curved surface in the 3D space. First, in order to carve out the approximate target surface from the whole 3D space, we use existing method to estimate a coarse depth map from viewed images. Afterwards, we focus on the neighborhood of the target surface and use our point flow module to refine the depth map, which saves us unnecessary computation. The refinement can be performed iteratively. First, we unproject the coarse depth map into 3D space to get the initial point cloud. Then our point flow module refines the position of each point by predicting the displacement to the ground truth surface, which we call point flow. So how to predict the flow to the ground truth surface? We augment each point with the features dynamically fetched from all the views by projection. Further, in order to help the modeling of network, we propose point hypothesis that we generate a sequence of points with different offsets along the reference camera direction and fetch features for all the points. Then, we use H-count to predict the probability of each point hypothesis, and the point flow is predicted as the expected offset. Now let's see some results. On the DTU benchmark, which contains 49 views per scene, our method outperforms both the traditional methods and the linear-based method. Compared with MVS-NET, the depth map resolution of our method is almost 5 times, while our memory consumption is even smaller. As shown in this figure, our method can reconstruct more geometry details than state-of-the-art. Also, compared with traditional method, our method can get more complete reconstruction. Moreover, thanks to the flexibility of the point cloud representation, we can choose to only refine the depth in the region of interest instead of the whole depth map. So here is the conclusion. The target surface of multi-view stereo is sparse in the 3D space. Our point MVS-NET is able to process the surface points directly, achieves better time and memory efficiency. Moreover, the refinement can be performed iteratively. For more information, please visit our project page. Okay. Okay, thank you for your time.
Could the Q&A be displayed? Thank you. So if you have any questions, please come to the mic. All right, so I'll start off with a question for the first speaker. You mentioned using synthetic data I'm just wondering how the domain gap between synthetic and real has an effect on the results.
So if purely trained on synthetic data as YCB, so the first of the two data sets, even if it has like a large number of samples, it can do something, it did something, but we noticed that there were still problems to generalize to more complete data. That's why we introduced the second mixed semi-synthetic data set.
I see. Any questions from the audience? Yep.
Hello. The question to the first author. You said that your enhanced TSDF could be fused several times from several viewing points. But what if the prediction of the inner surfaces was wrong? So when you rotate the camera, you will get -1 plus and +1 when zeroing the TSDF volume, and you will get a surface there. How did you handle this?
So most of the times we noticed that the thickness prediction was kind of both accurate, and best case scenario was actually in short with respect to the real back surface. So it's definitely might be definitely a problem in the case in which you have that you depicted. In general, I think that might be one limitation of the combination of using a predicted measurement and an actual sensor measurement. That requires a bit more reasoning about the uncertainties of predictions that, and a probabilistic mapping that probably will tackle that issue. But definitely, you could see some artifacts, I agree with you. So it's one of the limitations of the problem.
Yeah. Thank you.
You're welcome.
Any other questions? So I have a question for the third speaker. You went into the third speaker. Yep. So you went into detail about the memory efficiency, and you also in the final slide mentioned time efficiency. Can you just briefly comment on how much of a speed up you gain?
It's like the time consumption of a method depends on how many iterations you use. If you only use one iteration, it's about 0.8 seconds. I don't remember. But if you use three iterations, it takes about 3 seconds. But you can get a depth map of much higher resolution. Okay, our poster is at 26.
Okay, let's thank the speakers again.
My name is Xiangyu Xu. I will present the paper Discrete Laplace Operator Estimation for Dynamic 3D Reconstruction. This is a joint work with Andrea. We address the problem of reconstructing the temporally evolving 3D structure, given a set of asynchronized 2D observations with unknown ordering and arbitrary temporal distribution. Given such input, our goal is to determine the spatial temporal relation among our three observations. To this end, we propose a graph-theoretic formulation of the dynamic reconstruction problem. We define a complete graph where nodes present 2D observations. Node attributes are 3D geometries. The H value are spatial temporal affinities. The graph's Laplacian define its topology in terms of pairwise affinity between our 3D estimates. We propose a framework for their joint estimation. We consider two input scenarios. First, for images without any sequencing information. We enforce motion smoothness through the Laplacian linear form, promote linear topology through the Laplacian quadratic form, while fostering high reconstructibility and reducing reprojection errors. For unsynchronized videos, we know the local sequencing for each video streams. However, we have no prior on their temporal distribution. In this case, we use 3D geometry estimates to infer a global sequencing through dynamic time warping. Next, we apply dimensionality reduction to determine a 1D line mapping of our 3D geometry. Finally, we enforce this global sequencing through the Laplacian quadratic form. We use the 3D joint position from motion capture data as ground truth structure and project them on 4 virtual and synchronized cameras as 2D observations. Compare our method with multiple state-of-art baseline method, the method requiring global sequencing and the method requiring local sequencing. Our method variants that require global sequencing, local sequencing, and no sequencing at all. We compare 3D reconstruction error under different conditions. In the condition of 2D noises, our method without sequencing can even beat the other method requiring global sequencing. In the condition of different frame rates, our method is the best when global sequencing is unknown. In the condition of dropped frames, it shows that our method is more robust to arbitrary temporal distribution. In the condition of missing joints, we also have the best result in all scenarios. We also did experiments on real multi-well imagery. For example, reconstruction of a juggler whose motion is repeating. And reconstruction of a climber based on independent images. Finally, reconstruction of a person skiing, and our method doesn't enforce an object model. We consider the case of a reconstruction of spatially co-located but temporally disjoint events captured in a single aggregated image set. Our method will first define a complete graph where each node corresponds to an image observation. After optimizing, our method will output the Laplacian matrix corresponding to the topology of the structure. Each node will connect with its adjacent frames. After reordering the matrix with background truth sequencing, it will be close to diagonal. For such a scenario, we obtain a Laplacian matrix describing a graph with multiple connected components, one for each event. Spectral analysis of the Laplacian matrix visualizes the chain-like topology of each event. We have released our code. We'll come with our poster for more detail.
Hello, I'm Nathaniel Chodosh, and I'll be presenting Deep Non-Rigid Structure from Motion on behalf of Chen Kong and Simon Lucy. In this paper, we focus on one challenging problem. Imagine that we have a set of images from the same object category. Further, imagine that we have annotated or detected 2D correspondences across these images. We aim to explore how to reconstruct the 3D positions of these points with no prior 3D knowledge. First, we observe that the whole object category can be viewed as a single non-rigid object. For example, these instances from the category chair. Each object in isolation is rigid and can't deform. However, if we consider all the shapes as a single non-rigid object, then these instances can be viewed as deformations from this one general shape. Based on this insight, we can then use non-rigid structure from motion to solve the problem. We approach this problem with this optimization function, where W is the 2D points, S is the 3D structure, and M is the camera matrix. And omega is a penalty that enforces that S be multi-layer block compressible. Different from the classical non-rigid structure for motion algorithm, this paper proposes an innovative encoder-decoder neural network. Given the 2D correspondence is W, we apply 1-by-1 convolutions to estimate the block sparse feature, capital psi n. Then we use a fully connected layer to estimate the camera and hidden feature, lowercase psi n. And then with another sequence of 1-by-1 convolutions, we reconstruct the 3D shape, S. We label the blue part the encoder and the red part the decoder. Note that these learned parameters, D1, D2 to Dn, in the convolutions are shared between the two layers. This is because the whole architecture was derived as viewing it as a solution to an appropriate block sparse coding problem. And we invite you to see our paper for more details on this derivation. We first evaluated our method on the Pascal 3D Plus dataset. The y-axis here shows log normalized 3D error, and we've displayed here 7 state-of-the-art baseline methods in this task. And you can see that our method achieves considerably more accurate reconstructions than all of the baselines in all of the cases, sometimes by a factor of 10. Even when we add noise to the input, this performance gap still holds. And we have some qualitative evaluations from this data set in our paper. Next, we evaluated our method on the CMU motion capture data set. And in this, each video has tens of thousands of frames, and because of this large number, only these 3 baselines were able to successfully return results without crashing. And again, our method outperforms all others, sometimes by an order of magnitude. Additionally, our method generalizes well to unseen data, which implies potential utility to single image 3D reconstruction. Now we're going to show some qualitative evaluations of our method. Everything shown here just reconstructs per frame with no temporal priors, including ours. So we generate the videos just by concatenating all of the predictions together, and ours ends up smooth just due to the accuracy of the predictions. Finally, what we're showing here is some qualitative results on real images with hand-annotated images. We please ask that people view the journal version of this paper on arXiv for even more details. Thank you.
Hello everyone, my name is Songyou. Today I will present our work, Equivalent Multiview Networks. Equivalent networks have been explored in the past few years and are robust ways to deal with input transformations. However, they require specialized filters and features, which makes it hard to leverage all recent deep learning advances. For this reason, equivalent networks tend to outperform conventional approaches only in limited scenarios. In 3D object recognition, the most popular approach exploits the power of conventional science to extract representations of a 3D object from the set of its 2D views. The features from each view are then combined with max or average pooling. This operation is invariant to rotations, but not equivalent. We observed pooling discards the information and prevents the network from reasoning jointly over all views. We remove the view pooling and associate each view with an element of the discrete rotation group, visualized here on a solid of 60 pieces. This gives initial features that are functions on the group and equivalent to discrete rotations. How can we learn representations that maintain this equivalence? By using group CNN, we keep the features on the same group and maintain equivalence in every layer. This allows jointly and hierarchical reasoning over all views of an object. Our method combines the power of conventional scenes with the robustness of equivalent scenes. The largest rotational polyhedral group is the icosahedral group of 60 rotations, which is the usual domain of our features. If we have all 60 views, we construct input features directly. If we have either 12 or 20 views in a homogeneous space of the group, we lift them to the group via homogeneous space correlation. This, combined with a polar view representation that brings invariance to the in-plane rotations, allows equivalence to the full group with a reduced number of views. Localized filters allow hierarchical feature learning and computational efficiency. In our case, the filters live on the rotation manifold, so the support have to be selected using distances on the manifold. Here, we can see the receptive field increasing with the number of views. Different from conventional scenes, here we have to be careful about choosing the filter support. If all elements are from the same subgroup, the receptive field will not cover the whole input. We apply 3D rotations to the input and observe the feature map's equivalence. We began by applying a cycle of 5 rotations around one axis. Note that the features also rotate around one axis. Now we show a cycle of 3 rotations. The same holds for features on homogeneous space when using polar transform trick. We visualize the homogeneous space features on the faces of icosahedron and dodecahedron. And this holds for all 60 rotations of the group. In Shrek 17 3D shape retrieval challenge, we outperformed the previous state-of-the-art on both rotated and aligned datasets. This shows that hierarchical feature learning on group is useful even when global equivalence is not necessary. While we are outperformed on the ModelNet aligned classification, we do set a new state-of-the-art for retrieval and show a large gap over competing methods on rotated classification and retrieval. So far, we considered outside in-camera configurations, but we can apply the same method for inside-out, such as scene recognition. Instead of processing the whole panorama as a single image, we crop parts and construct a function on a cyclic group. This outperforms the baseline by a large margin. Conclusion, our method combines the power of conventional scenes with the robustness of equivalent scenes. It enables joint equivalent reasoning over multiple views. We surpass the state-of-the-art by large margin on several 3D shape analysis benchmarks. Thank you. Our code is available and our poster number is 29.
Okay, we'll have the Q&A session. Do you have any questions from the floor? Go ahead.
Hello, I'm curious about the last one. I want to know whether the equivalent theorem can be applied on any object that is not isomorphic to a sphere. Because you need to rotate your object and you project to such
In fact, we don't project to the polyhedral. We, like the multi-views, we just associate views with the element of the discrete rotation group. In fact, it is a multi-view method, but we use the group convolution to maintain this equivalence. Don't like the spherical scene project the object to the sphere. That's why we don't require the specialized filters and feature, and its accuracy is high.
But if your object has genus or something, how can you deal with that?
Sorry?
If your object has genus or something like that, how can you deal with that?
We just find the center of the object and render the views of the object.
Okay, thank you.
Thank you.
Do we have any other question? Okay, I have one question for the second speaker. So for the network, how do you decide the number of layers that governs the dictionary hierarchy? Is deeper better?
It's not incredibly deep, but I'm not sure exactly how Chen Kong arrived at that number, but I imagine it was through experimentation.
Okay. One more question for the first speaker. Can you say something about the computational cost, because it sounded like it's quite expensive constructing a complete graph and.
It's actually efficiency is a problem right now. It's for very large number of frames, it could be very slow, and that's what we are working on.
Okay.
Yes.
Okay, let's thank all the speakers again.
So good afternoon, everyone. This is Jia Geng from the Chinese University of Hong Kong. Today, I'm going to talk about our work on point cloud feature learning by interrelated convolutional networks. This is a joint work with Xiaogang Wang and Hongsheng Li. Previous works on point cloud understanding are mainly composed of 3 branches. Some works rasterize point cloud into voxels and apply to 3D convolutions. Other works project point cloud into images with multiple viewpoints and apply 2D convolutions. Pioneering works PointNet and PointNet++ directly handle point cloud data by bulk query and max pooling operation. And graph neural networks with continuous kernels are also applied in this problem. Our interpolated convolutions combine the spatially discrete kernels with interpolation functions to directly process point cloud data in a more effective and efficient way. So first, let's revisit the formulation of standard convolutions. Data points, for example, the red points are regularly distributed on the grid and with discrete coordinates. A convolutional kernel can be viewed as a set of kernel widths, and each kernel width has a 1/c width vector and a coordinate p prime relative to the kernel center p hat. However, in point cloud, the data points are no longer regularly distributed, and data point coordinates denoted as p delta are no longer discrete but continuous values. And if we want to apply the standard convolutions on the point cloud, we find that the kernel widths are not really overlapping with the data points. Inspired by the interpolation theory, once we have a data points falling into the neighborhood of a kernel width, we interpolate the data point feature f into the location of neighboring kernel widths. And the interpolation coefficients t are calculated by the coordinates of data points p delta and kernel width p prime. In this way, we can apply the standard convolution on those interpolated features. And in order to handle different point cloud density levels, we also add a normalization term n on each interpolated points features. We know that different from the standard convolutions in which the kernels had to be placed on the regular grids, in interpolated convolutions, the kernels are able to be placed at arbitrary locations. And during the convolutional process, the kernel is able to move freely on the object surface. And there are some choices for interpolation functions. In trilinear interpolation, we can interpolate a data point feature into a lattice of 8 kernel widths in the 3D space. We first normalize the distance and then use the inverse process of standard trilinear interpolation given this formula. Gaussian interpolation can also be applied in our convolutions. We define the neighborhood of a kernel width as a ball of 3 sigma radius, and every data point in the radius interpolates their features into the kernel width location given this formula. We should know that other interpolation functions can also be applied in our convolutions, as long as they are able to characterize the geometric relationships. And for normalization, we use the sum of interpolation coefficients for each data kernel width and we apply the normalization before we sum up all the results. In order to apply our interpolated convolutions on different tasks, we propose two template neural networks, named interpolated convolution networks. The classification network is a multi-branch architecture, and the convolutional kernels in different branches are of different kernel lengths. This kernel length is the distance of two kernel weights in the 3D space, and this hyperparameter controls the receptive field. With different kernel lengths, the network is able to capture both fine-grained geometric details and also global shape structures. The segmentation network follows the design of UNet and uses interpolated convolutions for downsampling. The kernel length becomes larger as the network goes deeper. We evaluate our approaches on ModelNet 40, which is a 3D object classification benchmark, as well as ShapeNet parts, which is an object part segmentation dataset. And the results indicate that our interpolated convolution networks show better performance compared with other approaches. We also evaluate our approach on Stanford Indoor 3D dataset. It is an indoor scene semantic parsing dataset. Qualitative evaluation shows that our approach is able to distinguish different types of small objects, and boundaries of different classes are clearer than other approaches. And here we show the visualization of feature activations learned by different kernels on ModelNet 40. Here we can see that different kernels are sensitive to different locations as well as shape patterns. For more details, please come to see our poster. Thank you.
Good afternoon, everyone. I am Michaela, and today I will be presenting our work titled Revisiting Point Cloud Classification, a new benchmark dataset and classification model on real-world data. In the recent years, deep learning techniques for point cloud data have demonstrated great potentials in solving classical problems in 3D computer vision. This was pioneered by PointNet in 2017, and multiple works followed then after. Among such problems is object classification, and several recent methods have reported very high accuracies on CAD model datasets such as ModelNet 40. The current progress on classification has also witnessed a trend of performance saturation, and this leads us to the question, is the problem close to being solved? Despite performing well on synthetic CAD data, we argue that point cloud classification is still an open problem and is far from perfection, especially when working with scans. Differences between CAD and scans are caused by object clutter, occlusion, brokenness, and background, etc., making the low-level geometry very different and learning more difficult. In order to show this, we introduced a new benchmark dataset for point cloud classification based on real-world data. We leverage on existing indoor scene datasets, SceneNN and ScanNet, to introduce ScanObjectNN, a new object dataset from real-world scans for point cloud classification. ScanObjectNN contains 15 common categories with 2,902 unique object instances. Our raw data is represented by a list of points with coordinates, normals, color attributes, and semantic and instance labels. Additionally, to further enrich our data, we introduce different object perturbations by perturbing the original bounding box. This is to introduce variations in background, object clutter, and partiality. All in all, our dataset has a total of around 15,000 objects with 6 different variants and 5 train and test splits. We also support part annotation for real-world scans. Our experiments show that even if point cloud classification performs well on CAD models, it is still a challenging problem when dealing with scans and achieves significantly lower accuracies. We conducted a comprehensive bench evaluation on existing point cloud classification methods on our dataset. That includes detailed comparisons of these methods. To discuss in more detail, object perturbations were done by randomly translating, rotating, and scaling the axis-aligned bounding boxes of the objects. From our experiments, we found that translation augmentation causes the strongest performance drop. Our benchmark also helped us recognize 3 open problems that are present when dealing with scan data. First, how to handle object partiality. For example, when scans are incomplete or when objects are occluded. Second, how to handle background points present when scanning the object. And third, how to generalize between CAD and scans. For example, training in one domain and testing on the other. We introduced a simple background-aware or BGA model to handle the problem on dealing with background. The idea is to classify only based on object points and not on the background. Hence, we have a classification and a segmentation branch, where the segmentation branch is conditioned on the learned intermediate class vector. We introduced BGA PN++ and BGA DGCNN that were based on 2 recent state-of-the-art methods. Results show that our BGA models achieve the best results on our scan dataset, and we have an online leaderboard, so please check that out. From our experiments, we also observed that DGCNN-based networks generalize better across the 2 data domains. That is, it has the highest performance when trained on synthetic data and tested on real, and vice versa. In summary, we introduced Scan Object NN, a new point cloud dataset on real-world scans that includes perturbation variants of varied difficulties. We also introduced BGA models as an initial solution to this problem. Thank you.
Hello, I would talk about point cloud silencing maps. Silencing map is constructed for images to characterize the contribution of each pixel value to the recognition result. We extend this concept to point cloud, aiming at studying importance of each single point. In this paper, we propose a novel way of characterizing critical points and segments to build point cloud silencing maps. Our method assigns each point a score reflecting its contribution to the model recognition loss. The silencing map explicitly explains which points are the key for model recognition. A point cloud silencing map can help us to better understand point cloud data. On one hand, if one drops points with the highest silencing scores, model performance would decrease significantly, endowing the potential to build an adversarial attack model. On the other hand, if only points with the lowest scores are dropped, model performance would not change a lot. Surprisingly, we found dropping points with the negative scores even leads to better recognition performance. Here, we will explain how to construct such a point-level silencing map, which is non-trivial. One possible solution is to drop all possible combinations of points and compute the loss changes after dropping those combinations. However, this simple brute force method is impractical because the computational complexity scales exponentially with respect to the number of points in a point cloud. Even only dropping each point and recalculating the losses are very time-consuming. In our solution, we propose an efficient method to approximate silencing maps with a single backward step through DNN models. The basic idea is to approximate point dropping with a continuous point shifting procedure, which is moving points towards the point cloud center. The intuition is that all the surface points of a point cloud are supposed to determine the recognition result, because those points encode shape information of objects. To verify it, we also provide proof of concept experiments in the paper. By approximate point dropping with moving points towards the point cloud center, prediction loss changes can be approximated by the gradient of the loss with respect to the point and a spherical coordinate system. After derivation, the silencing score can be calculated by the inner product of a vector from the center point to the point and the gradient of loss. It can be calculated by a single backward step through DNN models. Point dropping can be used to verify the veracity of our saliency map. We provide several point dropping algorithms as follows. A simple algorithm drops points for one time and then calculate saliency scores for one time and drop them, which might be suboptimal because point dependencies have been ignored. To alleviate this issue, an iterative version is proposed. The idea is to drop points iteratively such that point dependencies in the remaining point set will be considered when calculating saliency scores for the next iteration. A notable characteristic of existing technique like point net and its variants is their robustness to random point dropping. The robustness of point net comes from its max pooling layer, which only concentrates on a critical subset of a point cloud. The recognition result is mainly determined by those critical points, such that dropping some other non-critical points does not change the prediction. We propose point dropping strategies based on the critical subset theory. It just drops the points with the highest counts of the max put features iteratively. We use 3D Minist and ModelNet Forte to test our saliency map and point dropping algorithms. To test the performance of our saliency map, we compare our saliency map driven point dropping approaches to the random point dropping baseline and the critical subset-based strategy. The results shows that our method can always outperform those schemes in terms of improving or degrading model performance with limited points dropped. Our source code have been uploaded and open source on GitHub, and thank you for your listening.
All right. Are there any questions from the audience?
Yeah. I have a question to the first speaker, interpolation convolution. According to the paper, kernel length has a significant effect on the final performance. I guess the optimal kernel length depends on the density of the point set, right? However, density can be different at each input or locus of data. Is there any your insight about selecting optimal length or future idea to solve it?
The kernel length of interpolated convolutions are the hyperparameters you have to adjust, and it usually depends on the point cloud densities. And yeah, that's all. Okay.
Okay, thank you.
I have a question for the interpolation convolutions. How do you deal with rotation invariance?
In fact, this network is not rotation invariant. It's just like the standard convolutions, and they are all not rotation invariant. And you learn from different. If your data set composed of many cases that have rotations, you can learn it from your data set, I think. Yeah.
Okay, thank you.
Yep, go ahead. Oh, yes. So I have a question for the third speaker. With the point saliency maps. Yep. So you mentioned that dropping negative points can sometimes improve performance. So can you comment on qualitatively which kind of points get dropped?
Okay, by our algorithms, there are some points give negative contribution to the classification result. When we dropping these points, then the performance will be higher.
Right, but let's say you have an airplane. What kind of, like, which parts of the airplane usually get dropped?
for the calculating of the saliency scores, you can refer to the paper.
Okay, all right, thank you. All right, if we have no more questions, let's thank the speakers again.
Good afternoon. I'm Zhiyuan from Singapore University of Technology and Design. I'm going to talk about ShellNet, efficient point cloud convolutional network using concentric shell statistics. There have been several new networks for point cloud understanding, such as PointNet, PointNet++, PointWise, DGCNN, PointCNN, and so on. However, these networks are usually less accurate or require long training time. This motivates us to propose a lightweight end-to-end network which is both accurate and efficient. To achieve this goal, we propose a simple but effective convolution operator named ShellCon for point cloud understanding. Based on ShellCon, we further design an efficient end-to-end neural network called ShellNet, by which state-of-the-art accuracy and efficiency are achieved. First, let me introduce the ShellCon, which is a core component of the network. Given a set of points as input, we define a shell structure to perform convolution, which can efficiently output a feature vector. Here's an example of 4 shells, which covers a set of points around the key point indicated with different colors. The local points are distributed across the shells. From each shell, the representative features are extracted through the max pooling. Then the 1D convolution can be performed over the representative features of the shell from inner to outer. With this operator, we can extract effective features for a point cloud model. The red dots are the key points. On the right, big blue dots indicate the features extracted from ShellCon. Such operator has several advantages. First, it is invariant to point order, since the convolution is always performed along the direction from inner shell to outer shell, no matter how the point order is changed. Second, it can cover larger receptive field without affecting the speed, because we convolute over the representative features rather than the outer point features. And third, it is efficient and effective. The efficiency comes from the simple structure and less parameters, while the effectiveness is due to the larger receptive field, which enabled the operator to extract more useful information from the local area. Based on the ShellCon, we are able to design an efficient end-to-end neural network named ShellNet. The classification network consists of 3 ShellCon operators, followed by a classifier. The points are gradually downsampled into less representative points, denoted at blue dots with thicker shape indicates a higher dimension. So the output feature channels increase layer by layer. The segmentation network follows a encoder and decoder architecture similar to the UNet. We conduct experiments on both classification and segmentation. Here's the classification result on MONAD 40. The yellow rows show the accuracies of the ShellNet. We test with different shell size and achieve state-of-the-art accuracy with shell size of 16 and 32 with only 3D points as input. These 2 figures show the accuracy of point cloud classification of different methods over time and epoch. We can see that ShellNet outperforms all existing methods. It can achieve over 80% accuracy within 2 minutes and reach 90% accuracy on test dataset after only 15 minutes of training. We further analyze the network efficiency by number of training parameters, floating point operations, and running time. ShellNet perform best. Here are the segmentation results. ShellNet ranked first on SkyNet 3DIS and ranked second on ShapeNet and Semantic 3D. Here are the part segmentation results. Most parts are well segmented when very close to the ground truth. Here are the qualitative results on the indexing dataset. We can see that some failures are between wall and window, as these categories are quite similar in pure geometries, I may need other features like color or normal vector to improve. This is all-door semantic segmentation result on the semantic 3D dataset. The source codes are released. Please also visit us at poster 33. Thank you for listening.
Hello everyone, my name is Max Ovsyannikov and I'll present our work on unsupervised deep learning for structured shape matching, which is joint work with Jean-Michel Rufos and Abhishek Sharma from École Polytechnique. Given a pair of non-rigid 3D shapes, shape matching is about finding which points on shape 1 correspond to points on shape 2, or in other words, finding an optimal map or correspondence. This problem is important because once you have a correspondence, you can use it to transfer various properties, such as texture or segmentation, from the source to the target. You can also use them to perform deformation or animation transfer. We tackled this problem with the functional map framework, which is based on replacing a classical map T between points from shape S2 to S1 with a functional map T sub f between functions defined on S1 to S2 via pullback. This framework has been useful as it leads to simple optimization problems, is very scalable, applies to non-rigid shapes, and gets state-of-the-art accuracy without supervision. Typically, to estimate a functional map in practice, we first compute a reduced set of basis functions, then we compute descriptors and express them in the corresponding bases, and formulate an optimization problem based on preservation of descriptors and commutativity with the Laplacian operators. Finally, the optimized functional map is converted to a point-to-point correspondence. So now, the question is, what happens if something is bad in the early stages of this sequential pipeline? If you start with bad descriptors as input, you can easily get poor quality output, as is shown in the texture transfer example. FMNet, proposed by Litani et al. In 2017, tackled this problem by learning the descriptors. Given a pair of input descriptors, they feed them to a Siamese network and transform them to minimize the loss between the computed map and some given ground truth point-to-point correspondence. The problem with this approach is that this supervised loss requires ground truth correspondences and also computation and storage of pairwise geodesic distance matrices, which slows down the pipeline considerably. Therefore, the main goal in our work is to avoid relying on ground truth maps and also to avoid computing geodesic distances between points, thus working fully in the spectral domain. In other words, given a pair of shapes, we optimize for nonlinear transformations of their descriptors, and our main objective is to make sure that these optimized descriptors lead to higher quality functional maps. The main question is how to measure qualities of a good map. In this work, we construct an unsupervised loss based on 4 desirable map properties: bijectivity, local area preservation, near isometry, and having a functional map that is close to a point-to-point one. So as shown in this figure, we take descriptor functions as input and plug them into FMNet architecture. We then use the transform descriptors to estimate the functional maps in both directions. Finally, we exploit our new unsupervised loss to backpropagate and compute optimal descriptor transformations. As mentioned previously, our loss consists of 4 energy terms that we impose on the computed functional maps. Importantly, all terms are expressed in the reduced basis and are differentiable with respect to functional maps, allowing us to backpropagate to descriptor weights. We evaluate our approach on 2 benchmark datasets under 2 settings where we follow the train test split of Litani et al. Or do not split the data at all. We consider both original and remesh shapes, which makes the problem significantly more challenging. Among unsupervised methods, we outperform all techniques by a considerable margin, especially in the more realistic setting of remesh shapes, having different sampling and discretization. Here we show some qualitative results for texture transfer compared to existing approaches. When using the train test split, we get comparable results to FMNet, even though we do not use any ground truth information. Our method is also over 50 times faster since we work purely in the reduced basis. To summarize, we start with a bad pair of descriptors that, as you see, do not correspond to each other. We then transform them based on our unsupervised loss, leading to accurate functional and pointwise correspondences. Our source code is available on this link. For more details, please come to our poster session.
Hi, my name is Nadav. I'm going to tell you about this paper with this long name, for which we use the nickname quasi-branch and bound, or just quasi-BNB. The problem we're going to be discussing is called rigid alignment. So the input to this problem are just two shapes, and the goal is to find the rigid motion which aligns these shapes as best as possible. And this is typically done by minimizing some energy, which depends on the rigid alignment, so on a rotation R and translation T. Okay, our focus is on optimizing this problem and doing it globally. So we're less interested in algorithms such as ICP, which are very popular and fast, but they need good initialization to succeed. We're interested in a different class of algorithms, which does this globally. Typically, these are branch and bound algorithms. Their main disadvantage is that they are slow. And we're going to suggest a faster alternative, which we call quasi-branch and bound. And okay, we'll explain this, but we'll start out with explaining what the regular branch and bound does. Okay, so here we have a 1D example. We take the domain of the function, we partition it into intervals, and we evaluate the function once in each interval. And this enables us to compute upper bound and lower bounds on each segment. Now, using this, we can now throw out intervals for which the lower bound is higher than the upper bound, because we know that there's no minimizer in these intervals. So in this example, we're left with only two intervals which could possibly contain a minimizer. And then in the next step, we're only going to continue with these. What we're going to do is just partition them again, and then we do the process again. We compute lower bounds and upper bounds, and we optimize. And by continuing in this way, we can obtain, at the end of the day, the correct solution up to epsilon error. Okay, the quasi-branch and bound approach we suggest replaces lower bounds with quasi-lower bounds. What's special about quasi-lower bounds is that they don't have to necessarily be lower bounds in every interval. In fact, we only require them to be lower bounds in intervals which contain a minimizer. Okay, and this is still enough to maintain the global optimality of the branch and bound algorithm. We call this new algorithm quasi-branch and bound. And the main advantage of quasi-lower bounds is that, unlike lower bounds, which are proportional to the length of the interval, quasi-lower bounds are proportional to the length of the interval squared. This is essentially because the behavior at a minimizer is quadratic. As a result, we can actually prove that the time complexity of achieving epsilon accuracy with quasi-branch and bound is logarithmic in 1 over epsilon, while the time complexity of branch and bound is polynomial in 1 over epsilon. This capital D here is the dimension of the rigid motion space. The practical meaning of this result is that when we want high accuracy results with a very small epsilon, quasi-branch and bound will be much faster. Here's one example where you can actually see this, including the asymptotic rates in practice in comparison with the branch and bound algorithm of Lee and Hartley. And here's another example where we compare with the Go ICP algorithm, popular branch and bound algorithm, and here the x-axis is epsilon, the y-axis is time, and you see that for 10 to the minus 4, epsilon 10 to the minus 4, you get 6 hours. For 10 to the minus 6, Go ICP can take several days. And in contrast, the quasi-branch and bound takes up to 10 minutes, no matter what accuracy you choose. And future work, we'd like to try to use quasi-branch and bound for other problems where branch and bound has been successfully used, and hopefully can get improvements there as well. I'll be happy to talk about it in the poster session, poster 35. Thank you.
Okay, do you have any questions? Yeah. Please go ahead.
Yeah, I have two questions to the shared convolution. First question is, PointNet++ has multi-scale technique, and shared convolution looks similar to that, but more powerful. I guess the difference is PointNet takes all points in sphere, but shared conv is not, right?
I think there's a distinctive difference between PointNet++ and ShellNet. Because ShellNet, we use a shell structure, and from each shell, we extract representative features. But for PointNet++, they applied PointNet locally. So I think this is a main difference. Also, we also use 1x1 and 1x(n) convolutions, but the difference is the structure, I think, is different.
Okay. Then how it can have benefit? Can you explain more detail?
You mean why it works so powerful, right?
Yeah.
I think the effectiveness comes from the because we divide the local area into a series of cells, and it covers a larger receptive field. I mean, locally, it covers more points. So for more points, we can capture more information, and we divide the local area into several cells, so we can do a convolution from inner to outer. So this structure is the main point of the structure.
Yeah. Second question is, you emphasize the order of convolution. Is it affect on accuracy? If then why?
You mean the accuracy, right?
Yeah.
I think the accuracy for classification, we rank first, and for segmentation, we tested the performance on 4 data sets, and among 2 of them, we rank first. Yeah.
Okay, thank you.
Thank you.
Let's go ahead.
My question is for the third speaker. Can your algorithm benefit from the GPU parallelization?
That's a good question. Well, it depends in a sense. GPU or just parallelization in general?
I thought about the tree structure parallelization. Different tree branches could be computed at different GPU threads.
Right. Yes. So you could try. There's some interdependency there, but you probably could do something.
So that was my question, about interdependency. Yeah.
Yeah. Because the point of the branch and bound is to throw out things, so you do want at some stage to know what you threw out, but you probably could do it. Yeah.
Thanks.
Okay, we don't have time, so you can ask further questions at the poster, which will be held in the next room, D1. Let's thank all the speakers again.
Hi, I'm Peng from the University of Adelaide. If you feel confusing about this title, you can translate it as New Methods for Globally Optimal Robust Fitting. So model fitting is a common problem in computer vision. And in many cases, the input data contains outliers, which are abnormally distributed compared to the normal data. For example, in this figure 1, we show a typical case where we are given a set of feature matches between these 2 images, and we want to estimate the transformation between them. The transformation can be fundamental matrix, homography, or others. The outliers in this case are those red lines, which are wrong feature matches. Having outliers in the data can heavily reduce the performance of non-robust model fitting methods. Figure 2 shows a line fitting problem with one single outlier. We can see that the least squares returns the red line, which is highly biased even though we only have a single outlier. Therefore, we need to make model fitting robust, or in other words, insensitive to outliers. And one of the most popular ways in computer vision to achieve robustness is to solve the consensus maximization problem. Consensus maximization problem is NP-hard. Existing algorithms are either efficient but suboptimal, or globally optimal but impractical. This work improves the practicality of globally optimal methods by accelerating tree search, which is one of the most efficient globally optimal algorithms. Consensus maximization can be defined as problem 1. During tree search, each tree node is called a basis, which represents the solution of the optimization problem 2 on a data subset. Problem 2 is a tractable L-infinity problem, which the level 0 basis is obtained on the whole dataset, and each branch of a basis corresponds to removing a candidate outlier. The maximum number of children for each basis is D plus 1, where D is the problem dimension. The simplest tree search strategy is breadth-first search, which expands the lowest level basis first. A much more efficient strategy is A-star tree search, which uses admissible heuristics to greatly reduce the number of traversed bases. In this work, we propose 2 techniques to accelerate consensus maximization tree search without harming the global optimality. The first technique is called non-adjacent path avoidance. Remember that during tree search, the children of a basis can be traversed by removing candidate outliers and solve the optimization problem too. In this work, we show that some paths generated by such process do not lead to the children of the current basis. We call such paths non-adjacent paths since they connect bases between non-adjacent levels. Bases traversed by non-adjacent paths are redundant for tree search. The proposed technique is designed to remove such redundancy and accelerate tree search. The second technique is called dimension-insensitive branch pruning. As shown in figure 3, branch pruning was previously done by using efficient heuristics to check whether one of the branches of the current basis B must lead to the optimum solution. And if we can confirm that S2 is the one, we can safely prune S1 and S3 without affecting the final solution. In this work, we show that such technique becomes ineffective when dimension grows. The key observation for dimension-insensitive branch pruning is that as long as we know that one of S1 or S2 must lead to the optimum, even though we don't know which one, we can still safely prune S3 without affecting the final solution. This allows us to adaptively adjust the number of pruned branches, making branch pruning much more effective in practice. On synthetic data, we show that using our techniques, tree search can now handle a much larger number of outliers. And on challenging real data, previous methods could not finish in hours, whereas using our techniques, tree search terminated only in a few seconds. And in terms of branch pruning, previous techniques sometimes slow down tree search since too many failed pruning steps introduce extra computation. In contrast, our dimension-insensitive branch pruning was always effective. That's all for my talk today. Welcome to our poster session at 3:30 p.m. for detailed discussions. Thank you.
Hello everyone, thank you for being here. I'm Han Li from the Chinese University of Hong Kong. This is a joint work with Dr. Ji Zhao from TuSimple, Professor Jean-Charles Belgian from CAS, and my colleagues from CUHK. The title of our paper is Quasi-Globally Optimal and Efficient Vanishing Point Estimation in Manhattan World. Image lines projected from parallel 3D lines intersect at a common point called the vanishing point. Manhattan World holds for the scenes with 3 orthogonal VPs. VP has various applications such as 3D reconstruction, robot navigation. Given several lines in a calibrated image, we aim at clustering them by 3 unknown but solid VPs. VP estimation can be reformulated as computing the rotation between the Manhattan frame and camera frame. State-of-the-art methods are based on either sampling or search. However, they fail to guarantee accuracy and efficiency simultaneously. In contrast, we propose to hybridize sampling and search. Let's first consider the line fitting for illustration of the advantage of hybridization. Given a set of points corrupted by outliers, we aim at robustly fitting the line. Ransack in black failed to fit the inlier as 3. Brandon bound in blue is accurate but inefficient. In contrast, our approach in red first samples only one point as 1 to fit the line position, and then searches for the line direction. It retrieves all the 6 inlayers efficiently. Let's come back to the VP estimation. To compute 3 DOF of the rotation, we first use 2 sample image lines to compute 2 DOF. We then employ BNB to search for the 3rd DOF. 2 challenges exist. It's hard to divide 3 DOF due to their nonlinearity, and it's hard to compute tidebound efficiently. For computing 2 DOF by sampling, we use 2 image lines associated with the same or different VPs. To obtain such 2 lines, we conduct sampling several times. Accordingly, we hypothesize several rotations with respect to a single unknown parameter theta. In addition, we propose a strategy to improve the probability of valid sampling. We leverage the fact several nearly parallel image lines shown in red and blue are associated with the same VP. After several samplings, we search for the 3rd DOF. 2 problems exist. Among several hypothesized rotations, how to identify the optimal one. For the optimal hypothesis, how to obtain its optimal parameter. We tackle these problems as inlier set maximization. We conduct branch and bound to discard invalid hypotheses and also search for the optimal parameter. Our method is efficient thanks to our 1D search space and tidebound of our cost function. Our cost function is composed of the linear and quadratic trigonometric polynomials. We transform these polynomials into sine functions to compute tidebound efficiently. In the following, we present results on syntactic data. For accuracy evaluation, we fix the time bucket of our method to about 0.2 seconds and vary the time bucket of Ransack and J linkage. Given the same time bucket, our method achieves the highest accuracy. For efficiency evaluation, our method is significantly faster than branch and bound and is similar to J linkage. As shown in the left figure, at the 7th iteration, our method discards most the invalid hypothesis, and at the 9th iteration, it obtained the optimal rotation. As shown in the right figure, at the 9th iteration, our method discards most intervals, demonstrating that our bound is tight. This is the accuracy comparison on the Julca-Aguilar database that is a real-world data set. Our method shown in yellow outperforms J-linkage and Ransack significantly. This is a representative result. Ransack misses some inlayers, and J-linkage mistakenly clusters some inlayers. In contrast, BNB and our method both obtained the accurate result. In addition, for the cases that the BNB fails to handle, our approach obtains a correct VPs and also is more accurate than Ransack. The reason why BNB fails is that several outliers and partial inlayers define a fake Manhattan frame and BNB retrieve it. In the future, we will extend our work. We will focus on computing 1 DOF by sampling and computing 2 DOF by search. Thank you very much.
Hello everyone, I'm Yaqing. I'm going to talk about homographic-based process estimation with a common direction. This is joint work with Jianyang, Jin Peng, and Hui Kong. Estimating the relative camera motion from two views using the minimal points is a classical problem in computer vision. Efficient minimal solutions for different camera configurations have been well studied in the literature. For example, the 5-point algorithm for the calibrated cameras, the 6- and 7-point algorithms for the cameras with unknown focal length. However, previous study has shown that it is impossible to recover focal length from two views over a plane surface, since for any choice of intrinsic parameters, any homography can be realized between two views by some position of the two views and a plane. In general, minimal case solvers can be used with RANSAC in the 3D computer vision approaches, such as struck from motion pipelines. Using fewer points can reduce the number of iterations, but this usually requires additional constraints or assumptions. For example, it has been shown that if the gravity direction of the two views are known, the cameras can be aligned with this common direction, and then the relative rotation will reduce to 1 DOF. In this case, only 3 points are needed for the calibrated relative pose estimation. We will show that now it is possible to recover focal length from two views of a plane. Post estimation with known direction are largely motivated by the usage of smart devices, such as smartphones, tablets, which have accelerometers to measure the gravity vector. For the semi-calibrated case, it is reasonable to assume that the cameras have square-shaped pixels, and the principal points coincide with the image center. In addition, the IM and the camera are usually rotation aligned for smart devices. With above assumptions, our aim is to solve both the calibrated and semi-calibrated relative pose problems using homography. Suppose the plane is observed from two views. The 2D homography matrix G transforms one point into the other. Since the gravity vector can be calculated from the IMU readings, we can align the cameras with the gravity direction so that the Euclidean homography matrix can be simplified to HY. Now, we can obtain the relationship between HY and G. We all know that the essential matrix should satisfy the zero determinant and trace constraints. But there are no studies about the constraints on the Euclidean homography matrix. So we first illustrate how to find the constraints on HY. We define matrix Q, which is the difference between HY and the corresponding rotation RY. It is obvious that the matrix Q should be rank 1. Note that we need to add a scalar in front of the rotation matrix since the first part is up to scale. Hence, each 2x2 submatrix of Q must have zero determinant, and we may obtain 9 equations. Furthermore, we find that the rotation parameters C and S can be eliminated from the original equations. In this case, we finally obtain 5 polynomial constraints which are only associated with the elements of HY. Based on the constraints, we can build new minimal solvers with different camera configurations, including calibrated case, 2 cameras with unknown but equal focal length, 2 cameras where one is calibrated and the other focal length is unknown, and 2 cameras with different and unknown focal length. After HY is formulated with the parameters, we only need to substitute the formulation into the constraints, and all the problems will result in 5 polynomials with 3 unknowns, which can be easily solved using some online polynomial generators proposed by Gulova and Larson. As a conclusion, in this work, we explore the rank 1 constraint on the difference between the Euclidean homography matrix and the corresponding rotation, and propose new constraints on the simplified Euclidean homography matrix. This allowed us to derive new solvers which only need 3 or 4 points. Our solvers are corresponding to the standard 5, 6, and 7-point algorithms, and can be considered as supplement to the existing solvers. The proposed methods are largely motivated by the availability of smart devices, and our real experiments show quite precise results with an uncalibrated smartphone. Thank you for your attending.
Are there any questions from the audience? So yeah, if there are no questions, let's thank the speakers again and move on to the last two speakers.
Hello everyone, I'm Heng Yang from MIT. I'm glad to present our paper, a quaternion-based certifiably optimal solution to the Wobble problem with outliers. This is joint work with my advisor, Lucca-Aguilar. The Wobble problem seeks to find the rotation between two coordinate frames given vector observations. In computer vision, Wobble problem is also known as rotation search. Given 2 point sets with correct correspondences, the Wobble problem can be formulated as a least squares optimization. The Wobble problem has extensive applications across a lot of domains. Originally, Wobble problem was first proposed to estimate the attitude of satellites by measuring the direction of stars. Recently, Wobble problem has become a fundamental building block for many robotics and computer vision applications, such as object pose estimation, SLAM, manipulation, and panorama stitching. Although a lot of algorithms have been developed, there are still two challenges that remain unsolved. The first challenge is, in practice, a large fraction of outliers usually breaks existing solutions. The second challenge is, people have been developing algorithms without certificates, which means that these algorithms fail without giving the user any notice. This is extremely bad for safety critical applications such as autonomous driving. Before introducing our work, let me briefly summarize existing work. In outlier-free case, we have closed-form solutions for isotropic noise distribution and convex relaxations for mesh registration. In robust Wobble problem, RANSAC is the most popular paradigm, but it is non-deterministic and also fails in high outlier regime. M estimators are also very popular. However, they typically break at 80% outliers and provide no performance guarantees. Another popular paradigm is consensus maximization, which can be solved exactly using branch and bound. However, it takes exponential time. Recently, guaranteed outlier removal is shown to be an efficient and robust method. However, this method is also suboptimal. Our method, Quasar, which stands for quaternion-based semi-definite relaxation for robust alignment, is the first polynomial time, robust, non-minimal solver. The key contributions of Quasar are the following. First, we use the truncated least squares estimator to gain extreme robustness. Second, we show how to relax a non-convex problem into a semi-definite program with redundant constraints. Third, our algorithm is certifiably robust, which means that it solves the problem in polynomial time and either provides a certificate for global optimality or declares failure when the solution is actually suboptimal. Lastly, we show that empirically our solver is actually robust against up to 96% outliers. The intuition for using the TLS estimator is the following. We have a threshold that separates inliers and outliers. Measurements with small residuals are accepted as inliers, and measurements with large residuals are discarded as outliers. In the end, TLS estimation reduces to a least square estimation using only inlier measurements. Due to the high combinatorial nature of TLS estimation, it is very challenging to solve this problem globally. Therefore, our strategy is to first rewrite TLS estimation into a quadratically constrained quadratic program using a technique we name as binary cloning. And then we apply SDB relaxation and add redundant constraints to arrive at the convex SCP that we know how to solve in polynomial time. Please stop by our poster if you are interested in these technical details. We tested Quasar on the bunny dataset with over 90% outlier rates. Both RANSAC and M estimation fail badly in such high outlier regime. Gore also fails at 96% outlier rates. Our method Quasar, which is the blue box plot, is robust against all the way up to 96% outlier rates and returns the most accurate solutions. We also tested Quasar when the measurements are corrupted by very high noise. In this case, Quasar is still robust against up to 90% outliers, while all the other methods fail. In the end, we mentioned two potential applications of Quasar. The first application is image stitching in the presence of many outliers. As shown by the left image, a lot of outlier correspondences can appear when there is very little seen overlapping between two images. In this case, Quasar can still stitch these two images perfectly, while RANSAC fails. The second application is point cloud restoration, which goes to our RSS 2019 paper, where we have developed a solver called Teaser that decouples the estimation of scale, rotation, and translation, so that quasar can be actually used as a rotation solver. That's it for my presentation. Please come to our poster 39. Yeah, thank you.
Hi, I'm Tim, and I'll tell you about a theoretical result that's joint work with Kathleen Kohn, Anton Lakin, and Tomasz Pajla. So Kathleen, Anton, and I are mathematicians who work in algebraic geometry, and Tomasz is our resident expert in computer vision. The result is a complete list of minimal problems for reconstructing point line configurations in space. And I will try to explain exactly what that means. So the grand challenge that motivates our work is reconstructing the 3D world from many images. This has applications in 3D mapping from images taken by drones, in autonomous driving to localize and navigate cars in the 3D world, for tracking moving cameras, and for combining real and virtual worlds together, and in the movie industry to reconstruct 3D backgrounds. Our main task boils down to reconstructing cameras in 3D entities such as points and lines from corresponding 2D features. We assume calibrated perspective cameras. This means we have a pinhole camera with known focal length and an orthogonal coordinate system. So in the setting of calibrated cameras, we're looking for so-called minimal problems. The main application is that they're used in 3D reconstruction pipelines. What's relevant for us is that somewhere in this pipeline, we need to solve lots of small reconstruction problems in a ransacked loop. Each problem is a system of algebraic equations whose number of real solutions will vary, but the number of complex solutions is almost always the same. Most importantly, these equations depend on noisy data, and ideally, reconstruction remains feasible, even with noise. An important practical example of a minimal problem in computer vision is the 5-point calibrated camera relative pose problem. Here, 5 generic point correspondences in 2 calibrated views give exactly 20 relative poses over the complex numbers. Thus, we say this is a minimal problem with 20 solutions. Here's the definition. A problem is minimal if the number of solutions is finite and positive for generic or random image data. Remember that solution means 3D entities and camera parameters, so our definition includes the 5-point problem. To further illustrate the definition, here's a non-minimal problem where we have only 4-point correspondences. Here we don't have enough constraints. Generic data give us infinitely many solutions. Now, here we have another non-minimal problem, 6 points in 2 views. This time, the problem is over-constrained. So for generic or noisy data, there are 0 solutions. At this point, it's natural to ask, what are all the minimal problems that are out there, and whether we can somehow classify them all? Of course, we need to focus on simple 3D entities first if we want to gain any understanding. So the class of entities that we consider consists of points, lines, and some prescribed incidents among the points and lines. For instance, we might have used the window panes in these 2 images to match a point and 2 lines that are incident to it. So we answered this research question completely under one additional assumption, which we call complete multi-view visibility. This means that each point and line in space appears in each of the given images. So we proved that there are exactly 30 minimal problems in our setting of complete multi-view visibility, and we compute the number of solutions for each. So here, for example, we summarize the 5-point problem by giving the number of cameras involved, drawing the configuration of points, and giving the number of solutions. These are all of our minimal problems. Notice that for 7 or more cameras, we don't have any. Here I've highlighted the 5-point problem we've seen before. This next one is a degenerate case of the 5-point problem, which actually reduces to planar calibrated homography. These next 2 were discovered in a study of calibrated trifocal tensors previously. And last, I want to highlight some problems with few solutions that might already be efficiently solvable by state-of-the-art methods. So to conclude, There are exactly 30-point line minimal problems for relative pose estimation in a calibrated camera model with complete multi-view visibility. And for each of these minimal problems, we now know its difficulty as measured by the typical number of solutions. If you want to learn more about the result or the methods that we used, then please come to our poster. Thanks, and thanks to the chairs, and thanks to all of you.
Okay. I have one quick question for the first speaker. Can you say something about the computational complexity?
Yeah, so that's a very good question and very common question. So right now, the common problem for SDP is that it takes polynomial time, but it actually does not scale too well. And then we have, but this is not end of the story, because we can have actually two ways to handle it. The first one is to exploit the low rank property of the SDP and adopts the so-called Newman-Monteiro factorization to speed up the SDP. And then the second method is we can use some other solvers that gives a solution to the primal. And then we can use the semi-definite programming to actually verify the solution. So that's, in that case, it will be super fast.
I see. Okay. I also have one question for the second speaker. Do you have any concrete application scenarios that you have thought about for the newly discovered minimal problems?
It's not really the focus of our work. This image did come from a paper that wasn't ours, but yeah, we haven't thought through the pipeline of how you would match any of these sort of novel features. That wasn't really the focus.
Okay. Okay, so I guess you'll have more questions that you can ask in person at the poster session, which will be held in the hall next door, D1. Let's thank all the speakers again. And this concludes the session. Thank you.